Welcome back to BioB 160 Principles of Living Systems. I'm Ruth Reitzman, your instructor for the course. In the first unit, we discussed the levels of life, beginning with atoms and molecules that make up cellular structures. An example is shown in this figure, the structure of the chlorophyll molecule that is found in the chloroplasts of cells. In this unit, we'll explore the chemistry of life. We'll begin by looking at the chemical elements that make up living organisms, the ways they bond together, and the chemical reactions that occur in living systems. We have lots to talk about, so let's get started. Matter is anything that has mass and occupies space. Matter is composed of elements. There are 6 elements that are very abundant in living organisms. They can be summarized by the acronym CHNOPS, and each letter represents one of the elements. So C is carbon, H is hydrogen, N is nitrogen, O is oxygen, P is phosphorus, and S is sulfur. There are a few other elements that you should also recognize as important elements in living organisms. These are Na for sodium, Cl for chlorine, Ca for calcium, Cu for copper, I for iodine, Mg for magnesium, K for potassium, Fe for iron, and Zn for zinc. Be sure to learn the abbreviations for these elements, as we will be using the abbreviations in discussing chemical structures. From this table in your text, you can see the proportions of various elements that are found in the human body. You can see that 4 of them, oxygen, carbon, hydrogen, and nitrogen, make up over 96% of the weight of the human body. Other organisms have a similar makeup. The basic unit of matter is the atom. An atom is the smallest particle of an element. Atoms are composed of protons, neutrons, and electrons. The nucleus of the atom is made up of protons. They have a +1 charge, and neutrons that have no charge. The nucleus of the atom is surrounded by electrons that have a -1 charge. An example of an atom is shown here. This diagram shows the structure of a helium atom, which has 2 protons and 2 neutrons in its nucleus, and 2 electrons. The location of the electrons can be represented as a cloud of electrons or as circular orbitals around the atom's nucleus. Each atom can be represented by its atomic symbol along with numbers that provide information about the structure of the atom. The atomic number is the number of protons that an atom has. Shown here is the atomic symbol for C, carbon, and its atomic number is 6, meaning it has 6 protons. The mass number represents the number of protons plus the number of neutrons. So for carbon, the mass number is 12, meaning it has 6 neutrons and 6 protons. You can also number the number of electrons since it is equal to the number of protons. For carbon, the electron number is 6, since the atomic number tells us the number of protons is 6. This diagram shows an abbreviated version of the periodic table. The periodic table is a list of all of the known elements. The periodic table is grouped into vertical groups of elements that share chemical properties, and the horizontal rows that represent increasingly larger groups of elements. Isotopes are elements that have the same number of protons but different numbers of neutrons. One example is shown here. Carbon has 6 protons, but it may have 6, 7, or 8 neutrons. Isotopes often have different properties, such as radioactivity. Radioactive elements will spontaneously decay and give off energy in the form of rays and subatomic particles. This property is useful for biologists to trace elements and to date the age of fossils by their radioactivity. Our next topic is molecules and compounds. To understand how elements bond together to form molecules, we need to discuss electron shells, orbitals, and energy levels. In an atom, the number of electrons is equal to the number of protons. So if you know the number of protons, you know the number of electrons in an atom. Electrons revolve around the nucleus of an atom in orbitals. Different orbitals have different energy levels and are referred to as electron shells. The example shown here is neon. Neon's atomic number is 10, so it has 10 electrons. The first electron shell can only hold 2 electrons, and the other 8 electrons are held in the second shell. The outer shell electrons are called valence electrons. The outer shell valence electrons determine the chemical behavior of an atom. The periodic table of elements shows the electron distribution of each element. This figure shows the electron distribution diagram for the first 18 elements in the periodic table. Most of the common elements found in living organisms are shown here. If you look at the vertical columns, the groups of elements, you can see that each member of a group has the same number of electrons in its outer shell. This helps us predict the chemical properties for each group. Let's see how this works. Chemical bonds form between atoms to allow atoms to have complete outer electron shells. The first electron shell is complete when it has 2 electrons. All other shells are complete when they have 8 electrons. There are 2 ways to complete the outer shells. One is by sharing electrons and forming covalent bonds, or the second way is by transferring electrons to form ionic bonds. Each method creates an attractive force between atoms called a chemical bond. It is this force that holds atoms together to form molecules. This diagram shows 2 hydrogen atoms held together by a covalent bond. A covalent bond results by the sharing of a pair of outer shell or valence electrons. Since hydrogen has 1 electron in its outer shell, it needs only 1 more to form a completed shell. By pairing up with another hydrogen atom, each can share its electron with the other, creating a covalent bond. This figure shows several ways to represent a molecule of hydrogen, or H2. It can be represented with its electron distribution diagram, as a Lewis dot structure, as a structural formula, or as a space-filling model. The most common form that we will see in our diagrams is the structural formula, which represents the shared electron pairs as a single line between the hydrogen atoms. This diagram shows an oxygen atom, O2. Shown here are the electron distribution diagrams, the Lewis dot and structural formulas, and space-filling model. Note that oxygen has 6 electrons in its outer shell, so it needs to share 2 electrons with another atom to form a complete outer shell with 8 electrons. Since the 2 pairs of electrons are shared between the 2 oxygen atoms, the structural formula shows oxygen atoms connected by 2 lines. This diagram shows the covalent bonds between a water molecule, H2O. A water molecule consists of 1 atom of oxygen and 2 atoms of hydrogen. Each hydrogen is sharing an electron with the oxygen. This fills the outer shells of the hydrogen, which each needs 2 electrons, and also the outer shell of the oxygen. It needs a total of 8 electrons. The shared electron pairs are shown in the electron distribution diagram and the Lewis dot structures. The structural formula shows the shared electron pairs as single lines connecting the hydrogen atoms to the oxygen atom. A second type of chemical bonding is ionic bonding. In ionic bonding, electrons are removed from one atom and transferred to another. An example of ionic bonding is in sodium chloride, commonly known as table salt. The outer electron of the sodium atom is transferred to the outer shell of the chlorine atom. This creates 2 charged atoms called ions. Let's see how this works. In this diagram, we can see that the electron configuration of the sodium atom and the chlorine atom. The sodium atom has 1 electron in its outer shell, while the chlorine atom has 7 electrons in its outer shell. The simplest way for each atom to achieve a complete outer shell is for the sodium to lose the single outer shell electron and transfer it to the chlorine atom. As seen in this diagram, the sodium atom now has an overall positive charge, while the chlorine atom has an overall negative charge. The 2 charged atoms are called ions. Ions with an overall positive charge are called cations, while ions with an overall negative charge are called anions. This diagram shows sodium chloride, table salt crystal, in both the macroscopic view and the atomic view, with the packed sodium and chloride ions held together by their overall ionic charges. As we discussed in our first unit, when we move from a lower to higher level of organization, new properties emerge. In this case, the properties of each material, sodium, a soft metal, and chlorine, a toxic gas, are very, very different from the properties of the combined sodium and chlorine to form sodium chloride, as we commonly consume as table salt. In our discussion of bonding, we've seen 2 types of bonding: covalent bonding, in which electrons are shared, and ionic bonding, in which electrons are transferred from one atom to the next. In fact, some bonds have a bit of both properties. The electrons may be shared, but not equally shared. This unequal sharing of electrons results from the electronegativity of an atom. As shown here in this diagram of a water molecule, the attraction of the oxygen atom for the hydrogen's electrons creates a slight negative and slight positive end on the water molecule. Covalent bonds can be either nonpolar or polar. In nonpolar covalent bonds, electrons are shared equally between atoms. Nonpolar covalent bonding occurs in carbon-carbon covalent bonds. In polar covalent bonds, electrons are not equally shared, such as in the water molecule shown here. In polar covalent bonds, there are slight positive and negative regions of the molecules. We've spent a lot of time talking about chemical bonds, and now we'll talk about the relative strength of chemical bonds. Covalent bonds are very strong bonds. Bond strength is measured by the amount of energy required to break the bond. So it takes a lot of energy to break covalent bonds. However, weak bonds are also important in biological molecules because they influence the overall shape and flexibility of molecules. These weak bonds include ionic bonds, hydrogen bonds, and van der Waals interactions. Ionic bonds are the positive and negative attractions between ions, such as those found in a crystal of table salt, such as sodium chloride. Hydrogen bonds are a type of weak ionic bond. This occurs when two electronegative atoms, such as two oxygen atoms, two nitrogen atoms, or a nitrogen and an oxygen atom, are attracted to a hydrogen atom. Van der Waals interactions are weak forces created by the asymmetric distribution of electrons in an atom or molecule. This asymmetric distribution of electrons creates hot spots of positive and negative charges. An interesting example of the power of van der Waals forces is found in the interaction of a gecko's toe hairs and a flat surface, such as the surface of a wall. The van der Waals interactions are strong enough to allow a gecko to walk straight up a wall. In our tour of chemical concepts, we'll now turn our attention to chemical reactions. Chemical reactions often involve the making and forming of chemical bonds. In a chemical reaction, the starting compounds are called reactants, and the resulting final compounds are the products. An example is shown here. Two molecules of hydrogen react with one molecule of oxygen to form two molecules of water, H2O. In our discussion of the chemistry of living cells, we will look at several types of molecules and chemical reactions. One set of chemical reactions that is very important for the life of our planet is photosynthesis. In photosynthesis, the power of sunlight is harnessed to convert carbon dioxide and water into glucose and oxygen. This process can be visualized in the photos shown here of the water plant, Elodea, using photosynthesis to form sugar and oxygen. The oxygen released by the Elodea plant can be seen as bubbles forming on the surface of the plant leaves. We've covered a lot of ground in this episode. At this point, you should be able to identify the major elements found in living systems. You should be able to distinguish between the terms neutron and proton, protons and electrons, atomic number and mass number. You should be able to distinguish and discuss the importance of the following terms: nonpolar covalent bonds, polar covalent bonds, ionic bonds, hydrogen bonds, and van der Waals interactions. This concludes this section of BioB 160, Principles of Living Systems. To continue your study of this unit, follow the links for the MyLabs Plus Mastering Biology homework and post your questions and replies on this week's discussion board. Thanks and have a great day.